So I need to define linear independence. So a collection's the wrong word here, but it doesn't really matter. I'm using it in the colloquial English sense. So a collection of vectors. Oh, fuck it. Let's use the actual math. A set of vectors x1 through xn is linearly, you're going to hate this, dependent. If
that's what I do too.
There are A1 through AN numbers. What the hell? We can call this scalars. Is all comfy with this? Not all 0 with A1 x1 plus A2 x2 plus AN xn equals the 0 factor. Okay. I'm assuming we're gonna need some examples.
Yeah.
Okay. So, first example. Any single non-zero vector is going to be linearly independent. Oh crap, I defined linearly dependent. No.
The non-example. That is our solution.
These are linear, this collection, this set, right, with the one vector. This is your usual I vector for those in physics or Calc 3, right? So this vector cannot have this linear dependence property, right? Because if I thought about what that would mean that there was a non-zero number A1, right? So that A1 times 1, 0 was equal to the 0 vector. Is with me on that?
Yeah.
So if this statement is true, what do you know about A1?
Has to be 0.
Perfect. A1 must be 0.
Therefore, it's
Therefore, not all of the AIs, in this case, all of the AIs are 0, right?
yeah.
There's not a collection where not all of them are 0. So this set is linearly independent.
So
You guys with me on that tangled mess? Yes? Okay. So this collection is linearly independent.
Joe, you said any non-zero vector, but like, what if they're both one, and they could both be multiplied by 0? No, you're right. I'm so sorry.
It's all good. Don't worry, we need some more examples. So here's an example of something that is linearly dependent. So linearly dependent. I'm going to take the vector 1, 0 and the vector 2, 0. You guys with me on this? Okay. Why are those linearly dependent?
Because there is a set of scalars that multiply by the 0 vector.
Okay.
yeah.
Cool. There is a set of not all 0 scalars. So what is that set?
It would just be 1 and -0.5.
Okay, cool. So one option is 1 times 1, 0 minus 1/2 times 2, 0 is in fact the 0 vector. Is that the only such set? Why not? Why are you shaking your head so vigorously?
There's a lot of other numbers that can cause that.
Yeah, you could do -2. plus-
Yeah, one of the interesting things here is that if there's one of these little sets,
There's more.
there will be more.
Is there infinite?
It certainly seems like if I take this equation and multiply it through by any number at all,
It's
still true?
Yeah.
Okay.
So there's at least a one-dimensional infinity worth of this.
The book says many, and that bothers me because it's like, okay, many or infinite?
Okay.
Please tell me.
So, mathematicians tend to count with 3 numbers in linear algebra. The 3 numbers that you count with in linear algebra are 0, 1, and infinity.
Infinite.
So if it's more than 1, it's probably
I
infinity.
really wish they just say infinite.
So the reason they're not is they're kind of hedging their bets a little
I
bit.
can tell, like,
Big.
so there's like one example where it's like not, like doesn't make it infinity.
No, so in the context of this textbook, which is like real vector spaces, if there's one of these collections, there will be infinitely many. There are some contexts that are expansions of this concept where that might not be true. But they would be a different textbook that would be found in a different level of this course. This is one of those kind of, did I tell you guys this already? This is one of those courses that, like, there's the level that you guys are at, which is the, like, introduction to linear algebra, and then there's a second, often, kind of undergraduate level of this course, and then there's a third that's like a beginning graduate level course, and then there's often like a middling graduate level course, and then there's like an advanced graduate level course.
There's 5 different.
I mean, they're not all called linear algebra, but like 4 of them are. It's a little bit like Calc 1. So, you guys took Calc 1, right?
Yep.
So, there's a class called Advanced Calculus that's basically Calc 1 done over again with proofs at the junior level. And then there's a course called Beginning Real Analysis or Introduction to Real Analysis that's like a graduate version of that same class. And then there's another class that you take as a like early PhD student called Measure Theory, which is basically the same class but done again. And then there's Complex Analysis, which is the same class but with complex numbers. Math loops back and forth, and we just kind of like peel a little bit more of the like oversimplification off the top.
It's an onion.
Yeah.
It has layers.
Yeah. So you'll catch me like
Oh,
I'm kind of oversimplifying some things here, but most of this stuff is true. Interestingly, this textbook that you guys are taking this class out of, if you ask Melissa in the math lab, she has a copy of her own that she brought in because she used it to prep for her master's exams.
And she says that you can borrow it if you're in the math lab to use to study.
Yeah.
Go to the math lab.
Go to the math lab. Okay. That's not available for audiences on YouTube. Be sure to hit like and subscribe.
Oh, no, he did
Smash that like button! Smash
Just
that
for you,
subscribe and
Leo.
Ring the bell.
You need to stop
Okay.
putting it there.
So, yes, if there's one of these combinations, there will be more, infinitely many more. There's one more linearly dependent set that I should bring up right now, which is sets with a single vector in them are not always linearly independent. Can anybody give me a set with a single vector in it?
Say that again.
The zero vector.
Okay. So the set with only the 0 vector in it is linearly dependent.
Wait, is dependent?
Is
Yes.
dependent.
You can multiply by anything. It's still the
Yeah,
answer is
that's
Good. So all you have to do is supply it with one of the non-zero numbers.
100,000. Why not?
Sure. Pick your favorite non-zero number. I'm going to pick 7 because it's shorter than 100,000. But everybody with me on the idea that 7 times the 0 vector is still the 0 vector, ergo there is a collection of not all 0 A's.
Yeah.
Okay, now, are you all ready to get your heads slightly twisted off by one more weird linear dependence?
That's just the
Sure,
story.
why not?
There's no problem.
Alright. So, if you put the 0 vector in here, and any other stuff, actually let me stop there because I don't want to talk about what those two are linearly independent. So, here is a thing, right? That's kind of my I vector.
Yeah.
Here is the 0 vector. I'm kind of looking for 2 numbers, right, that I can put in here and get the 0 vector out of it. Can anybody supply me with a set of numbers that are not all 0 for this? Yeah, you can pick basically whatever you want for this one and 0 for that one. So this is where the not all 0 part of this comes in.
So underline all.
Yeah.
Okay.
As long as
Because-
one is not 0. Or
Yeah, as long as there is any one of them that's not 0, they are linearly dependent.
You figured out my problem. My problem was I thought you couldn't include 0 in the.
Yeah, that's often the trouble.
Yeah,
So,
that would have been helpful to know last night.
Yeah.
yeah, sorry.
Okay, we no problem now.
Okay, so let me add one example over here to the linearly independent side. If you had to pick another vector to be linearly independent with 1, 0, what would it be?
0, 2.
If you got to pick anything.
The 0 vector.
Okay, I think we just showed that if you put the 0 vector
Oh,
in,
wait.
it belongs over there.
Wait.
Because the
Fair point.
order of this doesn't matter, right? Everybody's with me on that?
Okay.
So, Leo wanted to put 0, 2 in, which is correct, but I'm gonna go with the classic choice of saying that the 2 vectors that I want to talk about are I and J.
Yep.
You guys all with me on that? I keep saying that. I keep pointing at this vector and saying I. Are you guys all good with that?
Yeah.
It's kind of the physics / calc 3. Okay, so I've got I and J. Why should these be linearly independent?
Oh.
Both have to be multiplied by 0 to get 0 vector out of it.
Okay, yeah, so we could think about that as, we could say, alright, so if we were constructing this, we'd be looking at A1 times 1, 0 plus A2 times 0, 1. This is supposed to give me the 0 vector. If I kind of compute a little bit on this side,
Both the scalars have to be 0.
that's going to give me the vector A1, A2, right? If the vector A1, A2 is supposed to be the 0 vector, then A1 has to be 0 and A2 has to be 0. So they are all 0. You guys good with this?
Yeah.
Okay. One more thing I'm going to say without really proving because we're going to end up using it later. Is that I'm going to write a statement here, and I want you guys to see if you can figure out what I mean. So, sets with too many vectors are always linearly dependent. Okay. So, what the hell does that mean?
I think I might understand what you're talking about. So let's say that we had a vector that only has two numbers in it, like the 1, 0. Right?
Okay,
And
so
the
we have a-
previous set.
So you're kind of saying, all right, we're going to talk about two-dimensional space.
Yeah.
Okay, cool.
So if we had that previous set, the 1, 0, and 0, 1, if we tried to add another vector to it, no matter what it would be, it would have to be either a 0 vector or a vector with a non-zero in either the upper or bottom position. And if it had that, then you'd be able to multiply it by a coefficient that would allow it to negate the other vector, either the top one or the bottom one.
Good. What if it was non-zero in both coordinates?
Non-zero in both coordinates.
Oh, you could find a scalar. So let's say we have I and j in. Oh wait, non-zero in both coordinates. So 1, 1 and negative 1, 1. You could just add those together and you get the 0 vector.
Okay, so you guys are claiming that what I mean by this statement is something along the lines of, if your vectors are two-dimensional, having more than two is going to be a problem.
Yeah.
Okay, so let me see if I can draw a picture to kind of guide your reasoning. Right? So, this is a two-dimensional space.
Yeah.
I'm going to draw a couple two-dimensional vectors. So, here's one non-zero two-dimensional vector. Here's another non-zero two-dimensional vector. You guys with me on that? Okay. Now, I'm going to draw a third. You guys believe that these two are linearly independent?
Yes.
Okay, so why do you believe that these two are linearly independent?
Scalar multiples of each other.
Good. They're not scalar multiples of each other. Why is that a criteria for linear dependence? Like, if they pointed in the same direction, why would they be linearly dependent?
Because they'd be the same thing geometrically speaking.
Yeah, but that's not really an evidence in this kind of weird-ass sum, right?
Mm-hmm.
You guys see that? So let me draw that case sort of separately.
Because you can multiply
So-
one by like negative and a scalar of the other and just
Good. So supposing I had this kind of purple vector and this black vector that I've drawn just slightly separated so that you can see them as being separate vectors. If I multiplied this one by its length divided by the length of the other one's length divided by its own length, that would scale it up to the same size. You guys see that?
Yeah.
So there is a scalar where I could get this vector,
And then cancel it.
and then I could reverse it. And then when I add these two vectors together, I would get 0. You guys see that? So, vectors lying on the same line are always going to be linearly dependent, because you can always pull this trick.
Yeah.
You guys see that? So, if I have these two vectors, these are not on the same line, I can't pull that trick off here. If I think about trying to get back to 0 by scaling these two and adding them together,
It's going to end up somewhere else.
yeah, like this one's always going to be pushing me kind of off to the side, right?
Yeah.
Yeah.
And so the only way for me to go out by some of these and then get back to 0 is going to be to go out by some of these and then go back on them. Which is really just going to be multiplying this thing by the 0 scale. You with me on that? So the problem is that if I introduce a third vector into this system, like say this guy,
Okay.
I very randomly picked that one. Could be any other vector. The scalars would be a little different. But this vector, this purple vector, lays in the plane made by the other two, right? So there's going to be some way I could, like, oh well, it looks like if I did this vector plus that one, and then just backed up purple,
Yep.
I could get back to 0. You guys see that?
One could just be a solid.
Yeah. I just have to find a couple scalars that add to negative purple.
Yep.
And then that'll be my kind of set. You guys see that? That'll be my scalars. Not all of which will be 0. Good with that?
Yes.
So this is kind of getting at the concept of dimensionality, but I don't really have dimensionality in a precise way yet. The reason I'm not doing this, I'm not saying this super, super loudly or proving anything here, is that this is going to be how dimensionality is defined later.
Okay.
So, like, I'm saying R2 is two-dimensional. Like, I'm going to continue to say that because I want to drive it into your head. It is two-dimensional, but it's two-dimensional because of this. This is how we define the word dimension later. You guys good with that?
Yeah.
That said, I want you to have this concept because I don't want you to waste a bunch of time when you have 27 two-dimensional vectors. I want you to be like, they're linearly dependent. There's too friggin' many of them. We're done. You guys good with this?
Yeah.
Okay.